So today we will switch gears a little bit and do something quite different from what we did yesterday and the day before. But before, let me make a few comments. Yesterday I did not have time to make them in the very beginning because we started in a rush. So I want to make a few comments pertaining to the first lecture and to the second one. So the first comment I want to make is that when we have this operator product expansion, we get, as we said, the leading term, which will be multiplied by the primary, plus a bunch of terms which are related to the descendants. And one thing that we saw very clearly was that by imposing that the OP inside the three-point function yielded the right result, we could fix all the descendants in terms of the primaries. So one important thing that I just want to emphasize, which is trivial, is that the more you go in this direction of considering more and more descendants, the more subleading these contributions are. Okay, so just something trivial, that these coefficients go like x to the n, they are very small if x is small. Okay, so the more you go to descendants, it's a bit like a dipole expansion, as we said. We have a dipole, quadrupole, octupole, and then you just don't care at some point. Okay, and you see the same thing at the level of the conformal block. What is the conformal block? It's a function that resums, that tells you what is the function where you sum a primary and all its family of descendants. And indeed, the leading term looks like a primary. And then you have a series of subleading powers in z and z bar that we know that they resum into the hypergeometrics. And they are just shifting a bit the spin and so on to get the descendant values. And they are subleading if z and z bar are small. They are an expansion. And the leading term is again the primary. Okay? So this is basic comment number one. Second basic comment is that when we have a sum over all the operators in the CFT, one of the operators that we could have is the identity. We can have the identity operator, the number one. It's an operator. It's a trivial operator, but we can have the identity flowing between the two operators. So in our examples, we could not, because if you would encircle two operators, if you would consider encircling two of our operators, the total, inside the sphere, you could count that you had some non-trivial charge. For example, we're considering the operator phi1, phi2, and phi2 bar phi1. What's the total net charge of this object? Well, from the two point of view, it has no charge because you put phi2 and phi2 bar, so that you don't care. But it has 2 units of charge with respect to phi1, with respect to the symmetry that rotates the complex scalar phi1 into phi1 bar. So therefore, when you encircle these two operators, you could not have the identity. However, if you consider some scalar operators, real scalar operators, and some correlation functions, say of 4 identical points, you can very well have a contribution where this point just goes to point 2, just generate a disconnected contribution where you connect O1 and O2. And then you connect O3 and O4. This could exist. You could have a 4-point function. One of the terms could be just a product of the two 2-point functions, right? So this would be totally disconnected. If you cut here, you see nothing flowing. And this is indeed what we see. If you write, let's write in the usual way. We strip out this factor, and then we write the identity is 1, because the conformal block is 1, if it exists, plus dot dot dot, and now let's look at this term that survived. It looks alright, because this is indeed the product of two 2-point functions. Each of these terms you can think as a product of two 2-point functions. Okay? So if it exists, and there's no problem in taking it into account. Okay, so these were the comments, and now the summary. What did we do yesterday? Yesterday, we computed correlation functions in perturbation theory to the leading order in perturbation theory, which was just 3 level. So we had composite operators. Each of our operators was made out of 2 fields. So we represent it as a point where 2 lines get out of this point. These are the 2 fields that made out the operator. And we studied correlation function of 4 of these guys. And when we compute this 4-point function, 1, 2, 3, 4, 1, 2, 3, 4, what we find is something very simple. There are 2 graphs, just a bunch of propagators. You strip out what you should strip out, and then the rest is just u plus v over u, which when written in terms of z and z bar was giving this. And then we have this beautiful rational function, and we do something a bit weird. We expand it as the infinite sum of this product of hypergeometrics, which is what we did. It looks a bit insane, but it's actually very useful, because then the coefficients of what multiplies the hypergeometrics, they have a physical interpretation. They are nothing but our 3-point functions of our operator OO going to OL. Right? Even that this formula is the picture that we just have a sum over whatever is flowing, and we have a product of 2 3-point functions. Okay? And if we were to sum, not only we find the 3-point functions, but we notice that it was enough to sum over dimensions equal to L plus 2. So just by doing this exercise, you would learn my theory as, if you start with only the scalar operators, you would learn that my theory has operators with spin. They have the energy equals spin plus 2. They have this interaction with my scalar operators. This is what we would have learned just by considering this correlation function of 4 scalar composite operators. Yeah? In this case, we could compare this with a direct computation. But I want to emphasize that in general, what we are going to do here, this is what is emphasized in this last comment, sometimes it's very tough to do. This is always more or less possible to do. You just write a 4-point function, expand, and analyze it. But actually, to compute it by brute force directly, even though it might look simpler, it's often much harder to do. For example, the starting point, we knew the form of a primary of spin L. Now, if I tell you, write me the primaries of spin L with 4 composite fields, with 4 fundamental fields inside them. It's already a very complicated combinatorial problem. It's a tough one. It's much tougher than computing a correlation function with more complicated composite operators, for example. But here we could write the primary. This is a primary. This is a normalization that we fix such that the 2-point functions are normalized to 1. And if we do, then the computation that we saw yesterday can be recast in saying that O spin scalar gives this green stuff times some factor that came out of the computation, and it was awesome that it came out because this is what it should be for a conformal field theory involving an operator with spin, and it was nice to see it coming out. And then, indeed, we are quite happy because this term is nothing but the square. This one is nothing but the square of this, which is a cross-check that everything is good, everything is consistent, and we understood what we were doing. Okay? Any question here? Is everything clear? Okay. So today, what we are going to do is some kind of AdSCFT appetizer or toy model. I actually forgot to check how much did John discuss about AdSCFT and what is ADS and what is... A little bit. No. He wrote the cylinder, no? No?
You mentioned the buzzword.
Okay. Okay, so give me 1 second.
So we related conformal to some isometries of AdSCFT?
That's right. So let me think how to introduce it best. So AdSCFT is a duality. So let's just draw a few pictures and then we'll go into the computation mode. So AdSCFT is a duality that tells you that there is some space-time there are several representations of this space-time, depending on which coordinates you choose to think in terms of. And this space-time is roughly a cylinder. It's a box. Antideciter is a gravitational box, in the sense that if you put stuff inside antideciter and throw stuff around, things go and then come back, and they keep moving inside this box. So antideciter is a gravitational box that you can think of pretty much like a cylinder, where particles move when they feel some gravitational potential and they come back in and so on. And this box, which is AdS, has a boundary, and the boundary of this box, depending how you foliate it, but if you foliate the full cylinder, the boundary would be R times the sphere, or Minkowski, depending on if you want to cover the full boundary or not. And the basic idea is that you can have a gauge theory, you can have a conformal field theory at the boundary of this space-time, which you think of really like a crystal ball, and then you put some probes on the boundary of this space-time. Okay, you kick this, you hit this boundary of this space-time, and then by hitting it, you excite stuff in the interior that propagates, smashes against each other, and so on, and you get something happens inside, and you measure the response on the other side of this cylinder, say. So this gives you a duality between computing correlation functions, in this case in our CFT, and in this particular case in R times SD, which we know then we can relate to flat space. We just saw in the first lecture how we go between cylinder and flat space, so it's not a big deal to have R times SD or to have flat space, right? And it gives you a correspondence between this object and some scattering process, some interaction that takes place in ADS. And the point is that this interaction contains quantum gravity. It contains strings, whereas here, the typical examples that we consider, we have some gauge theory without gravity. Okay. Now, there are other representations of this very same space-time that describe the physics just from slightly different coordinatization that gives you a different take on this duality, where you consider the so-called Poincare patch, where ADS looks very different from this, but it is the same ADS. It is just that it looks a bit different, the same like the seat, or you can cover in different ways. Where the boundary of ADS now is RD, which we know is related by Weyl transformation to S to, here it should be D minus 1. It's related by conformal transformation to R times the sphere. And then we have an extra direction, which is a radial direction. So we have our plane, our universe, and then we have some extra direction, and you have several copies of Minkowski spacetime becoming smaller and smaller as you go inside this radial direction. And the metric, here let me write it very explicitly, is the metric in Minkowski space, this dx square, but with some warp factor z squared that tells you that as you go inside, these copies of spacetime become smaller and smaller. And the boundary is at z equals 0. And the same kind of cartoons that we drew there on the cylinder in this representation would have the picture that if you consider some probes in your CFT, this should be described by some interaction that happens in this higher dimensional space-time. Some quantum gravity interaction would be dual to some correlation function in our CFT. Okay, this is again once more the cartoon, the same thing but with some slightly different coordinates. Okay, and today, by playing with a simple toy model, I want to show you that it does look reasonable that something like this could be true. Okay? So what I want to do is consider a very simple toy model. So first of all, are there questions about this general cartoonish blah blah? I mean, I'm sure you have already been to one talk on AdSCFT, right? You already heard this, all these pictures and all these words. Some of you might have even been to my colloquium yesterday. So is it okay? Can I move on to something more concrete that hopefully will make things also more clear in case this is not clear? Or do you want to ask me something about the general philosophy? I mean, I didn't prepare anything here. I can improvise a little bit if you ask me something. No? Is it because everyone is lost, or it's okay for the moment? It's okay? Very good. So now I want to do the following exercise. Let's suppose that here we have some quantum mechanical system, some quantum fields evolving. Let's consider a toy model where we have particles in this AdS spacetime with mass mi, which is large. And by this, what it means is that if you have particles which have a large mass, how do you describe particles in quantum field theory? Well, a particle goes from point x1 to point x2 by summing over all possible trajectories of the particle. This is what we learned from Feynman. And what is the weight of each possibility is exponential of minus mass times the length of going between x1 and x2. And this is what you are instructed to do in quantum mechanics, in quantum field theory if you want, if you think in terms of first quantization. You take 2 points, and particles move in space-time by going from point 1 and 2 in all possible weights, and the weight for each possible trajectory is weighted by the length of this trajectory. And if the mass is large, of course we know what happens. If the mass is large, we are in a semi-classical limit where a tennis ball goes around the classical trajectory. So if m is large, this just becomes a geodesic. Okay? So we want to consider a toy model example where we consider our space ADS. And then imagine that we kick ADS in 3 positions or 2 positions. And by kicking this, we excite some massive degrees of freedom. And these are going to be very massive degrees of freedom. So what they do is they propagate in ADS quantum mechanically, but because the mass is large, in practice we can describe them by some geodesics that go from one point to the other in ADS. So let's play a little bit with geodesics in ADS today. So today, the idea is we start with this spacetime, and we hit it at 2 points. Degrees of freedom go, and they propagate in ADS, but they choose the minimal length in ADS, which is a geodesic. And a geodesic goes inside. It's a little bit like, imagine you are inside the water and you want to go save someone and there is sand there. What do you want to do? You want to go to the sand, run in the sand, and then come back to the water again. You don't want to run straight. So here it's the same thing. This warp factor tells you that the lengths close to the boundary are huge. Right? The length close to the boundary is dz, dx over z. It's infinity. It's really very tough to walk close to the boundary. It's like, it's not really water. I mean, it's like running in honey. It's impossible. So you really want to go to the shore, go to the sand, run in the sand, and then come back again at the end and avoid being close to the boundary as much as possible, and this will be a geodesic. Okay? So now let's start then playing this exercise of trying to understand what theory, what would come out if this would be our rules of the game. So these are the rules that we are going to set. The rules are to study interactions between points, we draw geodesics between points and study geodesics to see what's the probability for something going from 1 to 2. And with these rules, we will define, say, what we call our 2-point correlation function between point x and y, which are points in RD. So we are going to use ADS to define what happens in the boundary and to see what theory comes out in the boundary if we use these geodesic rules as our rules in ADS. Okay? So far, we should not be biased and we should forget that we already have the title of this section. We should just imagine, okay, the rules is we have ADS, we have this classical description, and I want to see what description comes out at the boundary. I want to derive whatever it is. You should not be biased and guess that it is a CFT. You should be open-minded and see, let's see what we get. Okay? This is, we are not assuming anything. We are going to derive. So what is the, so first let me start with a statement that, first for simplicity, let's consider ADS2. ADS2 means that there is only one line and one radial direction z and one x. And the metric dx squared is just dz squared plus dx squared over z squared. So things happen in the plane. Okay? And we can put operators along this line, but it's like imagining that here I'm putting operators all in a line. I don't use the full R2, I just use the line to put my operators. And now, the first statement that I want to make is that geodesics in ADS are arcs of circle. Well, it's a trivial statement, you can check. So let me just state it, that geodesics are given by, let's write the equation for an arc of circle, z squared, let this point be x1, let this be the radius r1. So let's see if I can do this. So what is this? Z squared is equal to R1 square. What am I doing? So yeah, R1 square, Z square, plus.
There's a half-pH paper by some guy called Lopachevsky. Did this once.
No, I'm sure. Yeah. That's big news, yeah. And now you just confused me. Let's see. Let's see if this is correct. So when x, so this is not correct for sure. So now let's try to see. When x is equal to x1, this would give 0, z equal to 0. When x is equal to x1 plus 2r1, which is here, it's also 0. And the claim is that this equation here, where these are the parameters, and this is the variable, so this defines z of x. This solves the equations of motion that you derive from the Nambu-Goto action that describes the length of a particle, which takes the form in any curved spacetime. It is just, if you have some parameter that parameterizes your contour, you have square root of g mu nu in a given spacetime, x dot mu, x dot nu. Okay? And this is the length, right? This is nothing but integral of dx, the length of the curve, which is parameterization invariant. You see, I choose any tau. If I change from tau to f of tau, this expression is parameterization invariant. It's really the length of the curve. And in particular, I can choose tau to be x, the coordinate on the base of this curve, which is a useful parameterization, but I can use any other parameterization. You choose your favorite and solve the equations of motion coming from this action. This action that for this metric here takes what form? Integral d tau square root of z dot square plus x dot square over z. So you just take this equation, write Euler-Lagrange equation, find the geodesics, and you conclude that geodesics are arcs of circle. There are nice geometrical ways of seeing it, because ADS is also an hyperboloid. So this statement that there are many geometrical ways of understanding this in a straightforward way, but solving equations of motion is good enough. Okay? So this simplicity in these geodesics is the counterpart of the statement that, for example, in a sphere, geodesics are equators of the sphere. And this is exactly the analog, and in fact, ADS and spheres are just analytic continuations of each other, and this is really the direct counterpart of that statement. Okay? Very good. So let's try to compute then our example. Let's try to compute the length in this curve. So the first thing we see is that the length is going to be infinite, because as we said, the metric here diverges. So let's see this very explicitly. So let me tell you that you can now plug this expression for z, plug it there, and integrate. So let me write the following. Suppose, because this is going to be useful, suppose we consider half, okay, half of the arc circle. Why am I considering half? Because, you know, when you have square root, it's always the first part, the second part of the square root, it's always a pain. So let's consider the first half, then we know which branch we are talking about, and so on. And we never care. And then we consider a point here and a point here. Let's call this x final and this x initial. And now let's compute the length of this piece here, L. Okay? And you just compute. You just plug z to be equal to this expression, plug it there, and do the integral. Okay? Can I just write the result? So the result, L, is equal to 1/2 of logarithm of x final minus x1, x final minus x1 minus 2r1, x initial minus x1 minus 2r1, x initial minus x1. So you see that it is a log minus the other log that I just put together, which is the final point minus the initial point, the results of doing this integration. And now I have to debug because it's likely that I got something wrong. No, it's okay. Okay? So this is the length. And now you see what happens. And what is the total length? The total length, what we are going to do, the total length will be equal to twice the length of doing up to the top. Okay? And what we are going to do is we are not going to go all the way to the boundary, because this would be divergent. We are going to stop at some z equal epsilon. This is the prescription of AdSCFT. It tells you that you should actually stop epsilon away. And you can actually give an interpretation of this, as I will comment a bit later. But for now, let's just say that otherwise, this blows in our face. We put x initial equal to x1, and we can, I mean, okay, we are done. So for now, it's an obligation. We cannot do anything else. But actually, it can be understood. Infinities do appear in conformal field theories when you renormalize operators, and you can understand this epsilon as nothing but the analog of that renormalization. Okay? In other words, not other words, we will see. Okay. And then we can compute the total length. So our 2-point function, what is it? It's equal to e to the minus m1 length total, where this length total, as we said, is twice that length that we computed there, where x initial is x. Now you have to compute x initial such that z is equal to epsilon, and you do this computation and find that x1 is given by this. This tells you this is the position such that z is equal to a small epsilon at that point. You see that x1, xi is close to x1 by epsilon square, which makes sense. You see that the circle has infinite derivative. It really wants to get away from the surface as fast as possible. So when z is order epsilon, this happens very, very close to the point x1, much closer than the epsilon, so it's good. And x final is equal to? We are doing twice this point, so what is x final? I hear many x1s, many r's, and so on. Can someone? x1 plus r1. Very good. We start with x1 and x1, x1 plus r1, x1 plus 2r1. So the final one is x1 plus r1. Okay? And then something nice happens, which is that when you plug these values and consider small epsilon, that expression takes the form log r over epsilon to r over epsilon. Okay? And this is very nice because what is this? This is nothing but epsilon over 2r. Actually, there is a 2 here, so there is a 2 here. To the power 2 delta, where delta is equal, delta 1 is equal to m1. And here it's r1. Let me confirm that I did no mistake. Yeah. And this is a very nice result, because what is this? This is exactly what you expect for a correlation function of 2 points in a CFT. The separation of 2 points is 2r1. This is the separation between these 2 points. And you get the behavior. So what we get is r1, which is the 2r1, which is the distance between the points, to the point to some power. This is the dimension of the operator that we see is related to the mass of the operator inside. And then, of course, this was dimensionless, so this r better come with some other dimensionful parameter, otherwise it would make no sense, and this is why we needed to have this epsilon there. In other words, the operators that have no dimension, they will be UV divergent. And whenever you consider correlation functions in a CFT, you always need to multiplicatively renormalize your operators. You always need to take your operators, and if you compute some bare operators, O with O, you will always get a divergent result. You always need to define operator O, which is physical, as being epsilon to some power times the operator O. And then this physical operator, which is what we measure, is what gives finite correlation functions. So the fact that we get some epsilon to some power, you can say that this is just definition of my renormalized operator. If I say that this is computing the correlation function between some bare operator at x and some bare operator at x plus r. This equation is just telling me that the correlation function between the renormalized operator at x and the renormalized operator at x plus r is equal to 1 over 2r to the power 2 delta, where the operator which is renormalized is just defined to be epsilon to the power minus delta times what I call the bare operator. And this is just usual renormalization in a CFT. Multiplicative renormalization. Okay?
I'm sorry, could you repeat what you call by G2 here? This expression.
G2 is the correlation function between 2 points, defined like the definition. So you arrived late. So let me summarize. What are we doing?
I mean, just what's the exponent?
Yeah, okay. So let me start again. So what we were doing is, consider yourself lucky. We are doing the rules of the game were, we are saying that we have our space-time which is anti de Sitter, and we are considering the following interaction that will be induced at the boundary by the following rules. I suppose I have anti de Sitter, and now I kick the boundary at some points, x1, x2, x3, and so on, and by kicking this point I send geodesics in. This I can think of as saying that I'm exciting degrees of freedom in ADS, but they are very massive, so they propagate according to the equations of motion, and they follow geodesics. And then I ask myself, if I consider a geodesic, and I consider a geodesic between point x1 and x2, what would be the correlation function that it would induce at the boundary of this space-time if I use these geodesics as the dynamics inside my crystal ball? And why it is an exponent? Because it's always an exponent. In quantum field theory, describing the propagation between 2 points is the same as summing over all possible histories exponential of minus mass times the length. And if the mass is very large, this sum is irrelevant, and it becomes just e to the minus the mass times the minimal length. Okay. Any other question? Here? So these epsilons, the epsilons is definitely not the important message. I mean, these epsilons, I just want to demystify that they are nothing special. What is nice and very cool is that we get r to the power of delta. Is that we have a massive theory in ADS, we send some particle, and then, because of this wrapping factor and the fact that we have to run out of the HNA run and then come back, generated an effective interaction between 2 points that became logarithmic, and that gave rise to exactly the power law dependence that you expect in a theory, in a conformal field theory in a boundary. So this, if you want, is our first example where we start with dynamics in ADS, and this generated the effective kind of behavior that we expect in a CFT. We did not put this by hand, right? We are just starting with some geodesics in ADS, saying the rules of the game is a geodesic should go inside and come outside, computed the correlation, and it was that of a CFT.
So when one does renormalization with a short distance cutoff, one
Yes.
can get also divergences which do not come from, which are not universal, they come from relevant operators.
From what?
From relevant operators in the Lagrange, etc. Do you get those also in the...
From irrelevant operator?
From like the mass. I mean,
No, but that's not in a CFT.
If you do a short distance cutoff, it might happen because the short distance cutoff it has a scale. So you might tune relevant operators away from 0. If you do dimensional regularization, this doesn't happen. But with lattice spacing, it might.
But those is different, right? Those you renormalize away by counter terms.
Yeah. So
And these ones you renormalize by its multiplicative renormalization of operators.
yeah, but
So
the finite part, sorry, the prefactor of the correlation function might contain things which need to be tuned to 0 by counter terms.
That's true.
So do you see?
No, not in this. In this simple analysis, we don't see them. Here we only see the multiplicative renormalization. So what Marco is saying is that in a CFT, typically we have to renormalize many things. For example, if we have some coupling, this coupling can get corrections, and what we should do is measure some 3-point function, measure the coupling, that's the physical coupling, and then do experiments and so on. So there are normalizations of coupling, there is a normalization of mass, all those put divergences. This is another one. This is just that when you have correlation function, even if you already renormalize your theory, And if you consider correlation function of composite operators, you often get divergences that you associate to the composite operator itself, to the fact that you have a bare operator, that the operator itself needs to be renormalized if it's a composite operator. And the multiplicative renormalization of composite operators is what we are seeing here, not the other kind. But the other kind, I mean, I'm sure there are some models where you could try to probe.
So you would see them also in this kind of computation ideas?
Well, probably. I'm not an expert in this. I mean, I did this exercise I did yesterday night. I just. Sorry?
They will appear as boundary terms.
Yeah, that's right. Yeah. Right. Yeah. Yes. Yeah, I should say that, for example, when we consider doing fancier stuff and considering counter terms and renormalization in EDS and so on, for example, Rob is a big specialist in this. So much more than I do. And I am. Very good. And now, so any question here? So this you might think it's a little bit trivial, and I really find that something cool that I wanted to understand, so I prepared this for today, was to understand what happens when we have 3 points. Okay? 3 points is much more interesting. So let's consider we have our crystal ball, and at the boundary, we put operators at 3 points, x1, x2, and x3. Okay? And now we have some geodesics. Okay? But where? Where do they go? Well, now we can think that we have some geodesics. There are some arcs of circle. I don't know. And they meet at a certain point. Okay? P. And now we could repeat the same exercise. Let's study what is the net effect of considering these effective rules, where you integrate over all possible trajectories of particles that meet at a point. But of course, we know that what matters is the classical geodesics that go to that point. But nevertheless, this point is not fixed. You can move it around anywhere. And what you want to do is consider e to the minus mass 1 times length 1 minus mass 2 times length 2 minus mass 3 times length 3. And what you want to do is find the maximum of this quantity by moving the interaction point. Finding what interaction point gives the smallest possible exponent. And this will be the process that will dominate this interaction inside ADS. Is it okay? Good.
May I ask you?
Uh-huh.
Actually, why correlator is the sum of all these exponential trajectories?
Why, when we consider correlation function in a CFT, you can think of the correlator as the sum of this? Yeah. I don't want to explain this. This is first quantization. I can tell you a little bit more tomorrow before the lecture. Pass by. I mean, this will take me in the detour. I'm assuming you know this. I mean, it's a prerequisite for the course. It's quantum field theory, so I was assuming people knew this stuff. So if this is not familiar to you, I could tomorrow start 10 minutes earlier and review a bit of first quantization if people want. I mean, okay.
I'm familiar, but I just didn't see this particular form.
Mm-hmm. Okay. Okay, very good. Let me see if I could do it right away. It's a bit boring. You can do, but yeah, there's not much point, I think. Okay, so this is our problem that we have to solve. And what do we have to minimize? We have to consider what are the variational parameters is at which position xp this happens, and at which height zp this happens. there are actually two parameters, not only where, but at which height it happens. Okay? A priori, these are two free parameters, and for any point xp and zp in the plane, you can find some circles that intersect at that point. Okay? And finally, what do we need? What else do we need? What are these L1s? What are these L1 and so on? This L1 is nothing but this length that we computed here. Starting from where? From close to the corresponding point, for example, x1, x2, x3 for L1, L2, and L3, and going up to where? To xp, right? So starting here and starting at this point and going to this point here. And so let me just set up a little bit the notation so that this problem becomes tractable. Yeah, I should say that this kind of this problem, the first time I saw it was in a recent paper from 2 years ago by Romuald Yannick, and where he starts studying this kind of geodesics, and then at the end he ends writing down this problem and says this problem is very hard, if not impossible. So to find an analytic geodesic solution. So it's like when you want to convince a small kid to do something, you say, you cannot do this. Okay. So what do we have? We have this problem where Li, or let's write L1 and then we do the other ones, where L1 is equal to 1/2 log, let me copy what is written in the other blackboard, xf minus x1, xf minus x1 minus 2r1. By the way, is it correct what I wrote? Yeah, this looks more correct than the one I wrote before, actually. Yeah, I suspect this cannot be right, because the length should be very big when xi goes to x1. Let's see, when xi goes to x1, this will be log of 0, which is minus infinity. No, there is a wrong sign here. Okay, sorry. So we have this expression. This is the length we are going to use. So let's be very explicit to know what we should do. We have this problem where what is x initial? X initial is x1 plus epsilon square over 2r1. What is x final? X final is xp. You agree? And finally, what is r? What is the radius of this circle? So you see that the radius of this circle is a geometrical parameter. Once you fix this point, there is no ambiguity in telling what the radius of the corresponding circle is. Right? So you just drop Pythagoras theorem many different ways or whatever, I don't know. I forgot how I did it, but I'm just going to write, and this follows from some Pythagoras stuff. It's just x1 minus xp squared plus zp squared over 2 xp minus x1. Okay? So this is R1R. If you tell me XP, ZP, and X1, you tell me the point where it starts, the point where it intersects, I know the circle, I can fix R. Is it okay? So this is what L1 is. Similar expression for L2, similar expression for L3. Let's denote all this here by minus the action. We have e to the minus the action. This would be the action. And then finally, this is the problem we want to solve now in mathematics in the remaining 5 minutes. The problem is we have our action, which is m1 L1 plus m2 L2 plus m3 L3, where when you do all those replacements and the dust settle, actually these L's are very nice. This L is logarithm of x1 minus xp squared plus zp squared over epsilon ZP. It's not here. Good. Okay, and similar for L2 and L3. And what are we interested in? Our 3-point correlation function is e to the minus the action at the critical point. And this critical point is found by imposing that the derivative that this extremizes this action. Okay? So it's a trivial problem, right? Just take this, plug this expression for the L's, and find the minimum with respect to ZP and XP. Okay? And then this tells you what the correlation function G3, let's be more explicit, what is the correlation function between points x1, x2, and x3. Okay? This is the definition of my interaction in my boundary theory. And now I want to see how does it look like. The 2-point function, that nice form, how does the 3-point function look like? Okay. So let's solve that. Let's solve this. Any question? Is it clear or? So you will all have to rotate a little bit unless, yeah. Any question so far? No? So okay, so let's start then. Here is not yet a mathematical notebook. This should have worked right away. Let's see. I might have to change here something. Hi. No, I'm not sure if I am clicking correctly here. So there is here projector, and then there is this red or not red. Which one should it be? Huh? Sure. Okay. Sure, no worries. But ask me some questions in the meantime. Let's optimize this. No, this is a toy model. It's not something very serious. I could say, for example, it should be a scalar operator because I'm not putting any spin. I'm considering particles without spin moving inside the ADS. But then what's the precise map? What kind of operators am I describing? Why is this? Is there a precise theory that I'm describing? No, it is just kind of a toy model. I'm just trying to study some kind of correlator in some theory. I don't know what the theory is. I have no idea. I have no alternative derivation of this object here. So I'm defining the boundary. I'm defining the operators by their correlation functions. So I'm saying, let's define a bunch of scalar operators that are defined by what happens when I excite ADS at 3 different points. This defines some theory, some holographic theory, and we are starting to see how this theory looks like. And what we saw is that this mysterious theory looks like a CFT for what 2-point functions are concerned, but now for 3-point functions, it could give something totally different. We are going to see. But we are defining the theory through this ADS picture. Wow, this is extremely awesome. So let's do a few computations just to warm up to make sure that, also because we have lots of time. Let's, for example, see how this result comes about, just to see that it's nothing very mysterious, this result here. So what are we saying? We are saying that we just have square root of R1 square plus minus x minus x1 minus R1 square. This is our z, right? We have derivative of z square plus 1. So if we choose the coordinates where x is the variable, x dot is 1, right? We have z of x and x of x is just 1. So we just consider this. We take the square root of this and we divide by z. And we full simplify. And we get this, and then we just integrate this expression from x, from some initial value to some final value. And this is the integral, the result that we have here. Okay? So nothing special, so it is what it is. Now let me spare you the details of going through all this shenanigans of substitutions, and let's go directly where? Directly here, where we write down that we want to minimize this. So let's write our action. Our action is m1 times log of, say, x1 minus R1 square plus ZP square over, XP square over ZP epsilon, okay, plus the same thing for M2, X2, plus the same thing for L3. Yeah, is it clear? This is what we want to do. Okay, so this is our action. This you saw already, right? The first line. If you know me, you know I'm addicted to erasing stuff. So very good. We don't care about that anymore. So now we have, here is our action. Okay. And now what we want to do, we want to minimize this equation, so we want to generate some equations. And the equations are just the derivative of our action with respect to ZP. This is going to be equal to 0. And the derivative of our equation with respect to XP should also be 0. Okay? So these are our equations, and we can make them look a little bit nicer. Okay? So our equations is that the first line should be equal to 0, the second line should be equal to 0. So presumably this is why Romuald was saying that this should be almost impossible problem to solve, because it looks a bit tricky to equate this and this to 0. You see, it's not an obvious, if you look a little bit, it's not obvious that you can solve. You see, it's a very high order polynomial in ZP and XP. It doesn't look obvious that this will work. So let's try. Let's just ask our equations and let us solve 0 equal to our equations for xp and zp. Okay. Now we have to wait. And you can wait and wait and wait, and she will not finish. But now you do something fun. You say, okay, let's do the following. Let's say that M2 is alpha M1, and M3 is beta M1. Okay, we lose no information. But now M1 factors out, of course. We are just measuring all alphas, all M's in terms of M1. Of course, this should not matter. If mathematics was smart enough, this should be totally trivial, right? So this is really silly. But we define these equations too, and now we solve. And now we solve these equations where we have alpha and beta. You might not be convinced, and now it solves. Okay? So this is the intersection point. This is where these geodesics meet, at this point xp. This is where they meet at this point zp. Here. Yeah, but then the square root is negative inside, the i's cancel, everything is good. It's complicated. Right? Looks a bit scary. It's complicated, and indeed it's what it is. We can simplify a little bit, power expand, simplify a bit more. And this will be our solution. Okay, a little bit better, but still quite complicated. Okay, we don't want to see this, it's too scary. So now we have our action, and all we have to do is replace our solution there. So this is our correlation function of 3 operators at point x1, x2, and x3. Okay?
Here's another thing. You mentioned that something that you mentioned that can it happen that such point P just doesn't exist, for example?
Yeah, actually it could. Yeah, this could be a good question. Yeah. Does it always exist for any masses and so on? And if not, does it mean that there's no classical trajectories, but you have to go quantum and so on? But we will see. Let's massage this a little bit. It's not going to be so ugly forever. And now what do we do? Alpha goes back to M2 over M1, and beta goes back to M3 over M1. Okay, we don't want these alphas and betas anymore. And then this is what we have. Okay. And then we simplify. Okay. This power expand is indeed going to introduce i's, because power expand just tells don't be careful about signs and so on, and sometimes it gives some complex numbers, but that doesn't matter much. So let's this action critical, and action critical is given by simplifying and so on. Okay, and after simplifying, this is what we are getting. And this still looks very messy. Okay, so let's separate in, but we see already some log of x1 minus x2 appearing here, which is very nice. So let's do the following. Let's take our action critical and say, if you find log x1 minus x2, replace this by alpha log x1 minus x2, and do the same for the other ones. x1 minus x3, x1, and the same for x2 minus x3 and x2 minus x3. Actually, let me have a look at action critical once more before making sure that this makes sense. Yeah, it's okay. Okay, so we make this replacement. And now, so this is with alpha. And now the full result, let me just write it here. So the full result is the derivative of with alpha with respect to alpha. This is the part that has logs, plus with alpha, where alpha is replaced by 0, right? So I'm losing no information by this. I'm just separating the result into two parts. Either it comes with the log of x1 minus x2 or without. So if you compute, let's first do with alpha, when you put alpha equal to 0. So then we get something that doesn't depend on x1, x2, or x3 or anything. We can try to simplify it. I'm not sure if it will simplify much. It is just a complicated function of the masses. Okay? So this complicated function of the masses, whatever it is, I don't care. It's in the exponent. Let me just say that there is some constant here that depends on the masses. M1, M2, and M3. This, I don't care. It doesn't depend on the position of the operators. Okay? And now, but we can simplify it. It's possible to simplify a little bit. But this we are not interested. And now we do the other one, the part that comes multiplied by these logs. And now if we collect this with respect to logs, ta-da, this is the result that we get at the end of the day. So what is this result? This result is nothing but, now when you translate back to what it means for our correlator, it means that here we get x1 minus x2 to the power delta 1 plus delta 2 minus delta 3, and so on, exactly like we want for a conformal field theory. These are exactly the right factors. You see, x1 minus x2, m, remember, was identified with a mass with the power delta 1 plus delta 2 minus delta 3. x1 minus x3, delta 1 plus delta 3 minus delta 2. So all the three factors, they come out precisely as they should. And then there is some constant upstairs, which is the interaction of this process that between these three particles in this theory. Okay? So this is, I think, is a very cute toy model for AdSCFT. It's a toy model. We define some set of rules for classical particles moving inside ADS. We turn on the wheels. We solve this complicated optimization problem that is very well easy to state, but as you see, without this replacement of M2 by alpha M1, it would be impossible to solve. And you find a very nice theory in the boundary, which is nothing but a conformal field theory. Now, a modern point of view, typically we use it the other way around, AdSCFT. So let me go back to blah blah mode and tell you some philosophical remarks about AdSCFT. So AdSCFT is many things. It's a useful tool. It's a guiding for solving gauge theories. It's many things. But one of the things that it is probably our best definition. It can be used as a definition of quantum gravity. Okay? Definition of quantum gravity in the sense that you take your CFT in the boundary and say that my interactions in the bulk are defined by whatever my correlators in the boundary are. So this is exactly the opposite of what Lucy was asking. Lucy was asking, what are these operators? Here, it's the other way around. We were using the bulk to define some theory in the boundary. We were just saying, the rules are just these geodesics and so on, and this defines some theory in the boundary. But now we could imagine the other way around. Let's start with a theory at the boundary that we all know and love. Some theory will say that has scalar operators which are of large dimension. And let's compute their correlation function in the boundary. And what will we get? Well, by definition, by conformal symmetry, we will get this. But now we have a way of interpreting. We say, in our minds, what is going on is the following. I'm computing my correlation function in my CFT, and I get the result that I should get. And from this point of view of what is happening inside the bulk, how should I think of this? For example, if the particles have large dimensions. I should think that these particles in the bulk, they are some geodesics that are moving, and then they are interacting here. There is some interaction region where the particles are in the middle of ADS. They basically don't feel ADS. It's like flat space. And there is some process of quantum gravity of all these particles interacting, and it's really a process that we don't know about. And we define this process as saying, this for me is defined as the 3-point function in my favorite CFT, divided, if you want schematically, this is of course schematic, divided by the effect of this geodesic. So I strip out these geodesics, I take them out, this is just some trivial propagation. I divide by whatever this net effect is, I take out this factor, I divide by whatever this constant comes out of this computation, and the rest will be an order 1 constant that tells me when these particles get here inside, now there is some interaction part, some quantum part that we did not take into account. For us, it is just a trivial contact interaction. We were not putting anything interesting there. But now for general theory, it will not give exactly this. It will give this times something else, and that something else. From that something else, you are learning about interactions in the bulk of your dual theory. So AdSCFT, and the example that we did, as I said, would be a toy model where you consider three operators O, 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 with delta, where this delta is very large. And if this delta is very large, it corresponds to some massive excitations in ADS, and often they would be well described by these geodesics, and this would define the interaction of these excitations in ADS. So often, what we have when we say that I define whatever happens in the interior by my CFT, if you can show that in some limit you have inside, you have general relativity, then by definition, whatever comes out at the quantum level is your definition of the UV completion of the quantization of that general relativity. And this is a very powerful thing that I think is not well absorbed by the public, which is that, by the general public, which is that we do have a precisely consistent definition of quantum gravity that works through AdSCFT. And our best definition of quantum gravity is through these very simple quantum conformal field theories that I just told you about. But this is a toy model. Okay, this is kind of a toy model. More realistic, and by realistic I mean something where we do control better both sides of the duality, but something more realistic. The theory in the bulk is not a theory of particle, but a theory of strings. So typically, for example, what people are considering right now, which I find very, very interesting, is trying to solve the same kind of minimization problem, but where now particles, they are not particles, they are strings. So you form some kind of string minimal surface, and what you have to compute is not the minimal length, but the minimal area encapsulated by this string that approaches two given points. That is, now, instead of having a mass times a length, what you will get in string theory is e to the minus some tension times some area. This tension wants to push the string like the mass wants to pull the string. This tension wants to, if you have 3 points, it's like having a parachute. You put 3 points and the tension wants to stretch it. So this string wants to open up and to go to some minimal configuration that will look somehow like this. And now the problem for learning about heavy operators in a conformal field theory is finding minimal area surfaces that end on these strings. Okay? And this, we saw how simple it is for geodesics. Now you can imagine for surfaces and for finding the minimal problem with surfaces. And no such surface was found yet. However, we know the area. How? Using the fact that strings in de Sitter space, just this geometrical problem, compute the minimal area of strings. So you just write the area of a string in a hyperbolic space. You write Euler-Lagrange equations. There's no fancy string theory or anything. It's just the area of a surface in hyperbolic space, in ADS. These equations of motion are integrable. So this problem, despite being very hard, here, this can be tackled by using integrability. Okay? And this problem, for example, recently, the first complete computation of 3-point functions was done by Shota Komatsu, who is now a postdoc at PI. He did the first full computation of this full minimal area. Part of the result was done already by Yannick that I mentioned before. And they finished up what was missing, because basically in these more realistic examples, you have ADS times the sphere, and the sphere also contributes to this result, and it was important to finish it. And equally interesting, now you could imagine going on and playing other examples. What about even more complicated? What about a 4-point function that, as we know, is more juicy? I mean, this is really where we start saying, what about computing the area of a 4-point function? Did someone manage to compute the area of this animal and then start understanding its OPE and so on? And the most advanced computation in computing this correlation function was done by 2 colleagues of yours, by João Caetano and John Toledo, who are here students at PI. And they used some very powerful integrability technique to compute exactly the area of this minimal surface. And both for these 3-point functions and for these 4-point functions, of course, the results come out compatible with conformal field theory. They come out some nice results, in this case with some space-time dependence stripped out and then some function of the cross ratios, as it should. And whereas in our case, we were just playing with a toy model, here it better be, because here it's a well-established duality between a gauge theory that we know what it is and a string theory that we know, so here it had to work. But there are still many things to explore, even though they computed the area of this minimal surface. No one analyzed yet the expansion in the OP over what is flowing from these 2 points to these 2 points. It's an example of a very important open problem in trying to understand the structure of correlation functions in conformal field theories at strong coupling. So yesterday, we had turned off the coupling. The coupling couldn't be weaker. We were doing correlation function of composite operators at 3 level. So it could be either a free theory or an interacting theory at leading order in perturbation theory. And what we see today is an example of how, using AdSCFT analography, using these kind of ideas, how we can have a flavor of how sometimes correlation functions look like in theories that have holographic duals at strong coupling. So tomorrow we will go neither to weak nor to strong coupling. We will stay in a theory that actually doesn't have a coupling, and we will study the Ising model. We'll study the 3-dimensional Ising model, and which describes the phase transitions in water, and we will try to ask how can we compute those critical exponents of the Ising model using this powerful bootstrap equations that we wrote at some point as our definition of a CFT, but which we did not use yet. So that will be tomorrow. Very good. Today we finished 10 minutes later that we can use tomorrow. 10 minutes earlier that we can use tomorrow.